In the stillness of the cosmic night, where silence stretches between the stars, something unusual has begun to stir. An object once thought familiar has defied every rule we believed governed the heavens. In the past 48 hours, astronomers around the world have turned their instruments toward a single enigmatic visitor, the comet designated 3I Atlas. It has always been an unassuming traveler, one of countless icy remnants from the solar system's infancy, following its long, predictable path through the void. But now, that quiet consistency has been replaced by a storm of questions because something extraordinary has happened. Within a single rotation of the Earth, its light intensified almost sixfold. In only 6 hours, 3I Atlas became nearly twice as bright as even the most optimistic models predicted it could ever be. At first, the reports came from amateur astronomers, those patient watchers who spend their nights in backyard observatories, chasing faint smudges of light across the sky. They noticed the change almost simultaneously in different corners of the world. What they saw was not the subtle flicker of a routine outburst, but an explosive surge, a comet transforming in real time before their eyes. Soon, larger telescopes confirmed it. The Hubble Space Telescope, during an unrelated observation window, captured images that left scientists silent. The once familiar coma, the hazy shell of gas surrounding the nucleus, now blazed with asymmetric intensity. One hemisphere shone with nearly blinding radiance, while the other lay dim and subdued, as though some unseen hand had resculpted the comet overnight. For astronomers, light is more than beauty, it is language. Every shift in brightness, every spectral line, every photon carries a message from the cosmos, encoded in frequency and energy. When that message suddenly changes, so too does our understanding of what sends it. The mystery deepens because this increase in brightness was not the only anomaly. Instruments measuring rotational velocity revealed that 3I Atlas has slowed its spin from roughly 2.4 hours per rotation to just over 3. Such a change demands force, a torque acting across vast distances from the nucleus's center. But what could apply that force? In the emptiness of space, momentum is sacred. For a body to slow itself requires a push or pull, a breath of invisible power. Natural explanations usually suffice. Jets of vapor venting from frozen ices can act like thrusters, altering a comet's spin. But the data suggest that the outgassing required to produce this degree of change would be enormous, far greater than the modest plume activity actually detected. That contradiction lies at the heart of the puzzle. If nature cannot easily account for the effect, then something unusual must be at work. And the more closely scientists look, the stranger the story becomes. Spectroscopy, the art of dissecting light into its constituent wavelengths, reveals truths the eye cannot see. When researchers compared the new spectra to previous observations, they found something both thrilling and unnerving. An emission line at 637 nanometers had returned. It was last seen months ago during the comet's perihelion, when it passed closest to the Sun, only to vanish afterward. Now it glows again, brighter than before. Yet according to our current understanding of cometary chemistry, this wavelength should not exist. It does not correspond neatly to any known atomic or molecular transition found in common cosmic materials. Its persistence across multiple observatories using different instruments rules out simple measurement error. Infrared readings compound the mystery. Between 2.5 and 3.5 microns, new features have emerged. Signatures usually linked with complex organic compounds, molecules rich in carbon that form the foundation of life's chemistry. These emissions suggest either a profound alteration in surface composition or an active process generating such compounds in real time. Whichever the case, it challenges existing models. The comet seems to have awakened from dormancy, revealing hidden layers of itself. Or perhaps revealing something entirely new. Thermal data, add another layer. Before, the object's surface temperature was evenly distributed, warmest where sunlight struck, cooler in shadow, just as physics predicts. But now, localized hotspots glow roughly 50 kelvins above the average. This uneven heating defies the simple logic of solar illumination. Energy appears to be emerging from within rather than merely reflecting the sun's light. That raises an unsettling question. What could be producing that heat? Internal chemical reactions, crystallization processes, or something else? Something we have not yet defined? As these observations unfold, scientists are finding themselves confronting not just data, but their own expectations of what is possible. Space, so often portrayed as still and eternal, has revealed once again that it is capable of swift and bewildering change. And yet the most haunting aspect of this event may not be what we see, but what we do not. In the debris field trailing behind 3I Atlas, fragments expelled months ago during a violent outburst, subtle shifts in trajectory have been detected. These tiny pieces, once following predictable paths, now drift ever so slightly off course, as if responding to a shared impulse. Coincidence? Or connection? When one mystery aligns with another, the human mind begins to sense pattern, even before proof emerges. Could all these transformations share a single origin? A chain reaction spreading through the object's structure, or perhaps a system responding as a whole? No one can yet say, but as the hours pass and the data accumulate, the sense grows that we may be witnessing an event unlike any seen before, one that could force us to rewrite the boundaries between the natural and the artificial, the ordinary and the extraordinary. In this moment, under the quiet hum of observatories and the whispered excitement of scientists around the globe, a question rises like the comet's own luminous plume. Are we merely watching nature at its most unpredictable, or has something else, something not of this earth, begun to move among the stars? When the first detailed analyses of the event began arriving at data centers, the atmosphere among researchers was one of disbelief. The numbers defied every model. The rate of change was too abrupt, the correlation among multiple parameters too precise. What at first seemed like observational noise had solidified into a verified phenomenon, confirmed independently by observatories on 3 continents. The comet known as 3I Atlas had undergone a complete transformation, and now the race to understand what had happened began in earnest. At the Johns Hopkins Applied Physics Laboratory, a team of astrophysicists reconstructed the timeline second by second. At approximately 0312 Coordinated Universal Time, the brightness curve began its sharp ascent. By 0917, the magnitude had increased by 1.8, a sixfold surge in intensity. The Hubble Space Telescope confirmed these results while engaged in scheduled calibration observations, capturing images that revealed an unanticipated hemispheric asymmetry. One side of the comet emitted light and gas in torrents, while the other appeared dormant, almost severed from activity. The symmetry of natural sublimation had vanished. Simultaneously, spectroscopic teams at the European Southern Observatory detected the re-emergence of that elusive 637 nanometer line. When first discovered months earlier, it had been dismissed as instrumental artifact, yet this time the signal appeared clean, repeated, and verifiable. The wavelength corresponds to no known neutral or ionized species commonly found in cometary spectra. Hydrogen, oxygen, carbon monoxide, carbon dioxide, cyanide, hydroxyl radicals, all of these have well-documented signatures. But this feature, faint and red-shifted slightly from the known oxygen triplet, suggested a transition of a molecule or atom not catalogued in any current database. Infrared spectra from the James Webb Space Telescope, redirected in an emergency coordination effort, added further complexity. Between 2.5 and 3.5 microns, broad absorption and emission bands indicated the presence of aromatic hydrocarbons and possible amide groups. These are chemical structures linked to complex organic synthesis. Such compounds have been detected before in cosmic dust and meteorites, but never with such intensity or spatial coherence. On 3I Atlas, they appear localized to regions corresponding with the observed thermal hotspots, as though they were being actively produced rather than merely revealed. Infrared imaging also revealed that the surface temperature had risen by an average of 50 kelvins compared to earlier observations. In absolute terms, this represents an increase from roughly 200 to 250 kelvins, a temperature jump inconsistent with any known passive heating process. The energy required to produce this would exceed the total solar flux incident on the comet's surface by several orders of magnitude. That implies either temporary internal heating or a process converting chemical or electrical energy into heat. The anomaly deepens with rotational dynamics. The spin rate reduction from 2.4 to approximately 3.1 hours may seem minor, but it represents a substantial loss of angular momentum for an object tens of kilometers across. For such a change to occur, torque forces of extraordinary magnitude must have acted briefly yet efficiently. Natural jetting, caused by volatile gases escaping from subsurface vents, can alter spin, but not usually in such short timescales and never so uniformly. The deceleration of 3I Atlas appears global, affecting the entire structure rather than localized outgassing regions. To explain this, several research groups produced competing hypotheses. One proposed that the comet suffered a massive internal cavitation event, a collapse of hollow pockets within its nucleus, redistributing mass outward and altering moment of inertia. But this would typically lead to spin acceleration, not deceleration. Another team suggested that electromagnetic interaction with the solar wind might generate torque through induced magnetic fields, yet this requires conductivity and field strengths not observed in cometary materials. The lack of plausible mechanisms left scientists searching for a missing factor. Parallel to these physical anomalies, the debris field trailing the comet began exhibiting coordinated motion. Observers at the Mount Lemmon survey in Arizona and the Atacama Large Millimeter Array in Chile detected subtle but synchronous deviations in the trajectories of at least 6 major fragments. Each shifted velocity by several tens of meters per second within the same observational window as the main body's transformation. For fragments separated by thousands of kilometers to alter course nearly simultaneously would require either synchronized forces or communication between them. In known physics, only gravitational or electromagnetic fields could produce such coherence, yet no external perturbations of sufficient magnitude were detected. The situation reached a new level of complexity when radio telescopes searching for natural emissions reported a narrow-band transient signal centered near 180 MHz, lasting for less than 2 seconds. The signal was non-repeating and broadband analyses are ongoing, but its occurrence precisely matched the timing of the thermal spike recorded by Hubble's infrared sensors. Most researchers urge caution. Cosmic rays, terrestrial interference, or data artifacts can produce such transients. Yet the coincidence is impossible to ignore. NASA's Planetary Science Division released a measured statement acknowledging the event while withholding interpretation. The observed photometric, spectroscopic, and rotational changes in Object 3I Atlas remain under investigation, it read. Preliminary analyses do not yet indicate a singular causal mechanism. Further observation campaigns are scheduled. The tone was carefully neutral, devoid of speculation, but within the scientific community, the tension was palpable. Off-record discussions revealed deep divisions. Some researchers insisted that the phenomenon must arise from unrecognized natural processes, delayed sublimation, cryovolcanic activity, or internal fracturing releasing trapped volatiles. Others argued that the evidence for coordination and coherence across multiple domains, optical, thermal, and mechanical, pointed toward a controlled or systemic cause. Among those cautiously entertaining unconventional explanations was Dr. Amelia Reyes of the Institute for Extraterrestrial Systems in Madrid. In a preliminary briefing, she presented a mathematical model showing that if energy were being generated internally, the power output would approximate 3 gigawatts, comparable to the continuous output of a terrestrial power plant. That energy could account for both the brightness increase and the thermal hotspots. The challenge, she emphasized, is identifying any natural process capable of sustaining that level of output without rapid disintegration. We may be looking at catalytic reactions of a type not yet observed in comets, she said. Or we may be confronting something we don't yet have the vocabulary to describe. The possibility of artificial mechanisms inevitably surfaced. Some physicists proposed that if 3I Atlas contained metallic or composite inclusions capable of inductive heating, then exposure to the solar magnetic field might generate currents producing localized heat. Yet such materials have never been detected in natural cometary samples. Others speculated about piezoelectric effects from internal stress or unknown crystalline structures responding to solar radiation in nonlinear ways. Each idea attempted to reconcile the observed data without invoking deliberate engineering. Still, none could account for the simultaneous nature of the multiple phenomena. At the same time, the consistency among independent observations lent extraordinary credibility to the event's authenticity. Teams at Caltech, the European Space Agency, and the Japanese Aerospace Exploration Agency compared raw data streams and confirmed matching signatures. The 637 nanometer line appeared in all spectra, recorded with different instruments and calibration standards. The rotational deceleration appeared in radar echo measurements and in photometric light curves. The infrared anomalies persisted across all datasets. These were not illusions. Something had changed in 3I Atlas, deeply, coherently, and perhaps purposefully. Computer models attempting to simulate the transformation failed to reproduce the observed brightness evolution. Even assuming extreme outgassing rates, the resulting light curve rose too slowly. The observed rise, nearly exponential, implied a feedback mechanism, where increased heating triggered processes that further enhanced emission in a self-reinforcing cycle. That is characteristic of active regulation rather than passive reaction. In biology and technology alike, feedback loops maintain stability or drive transitions. Nature can create them through chemical kinetics, but rarely with such precision or speed. As data continued to pour in, astronomers began noticing faint structural changes in the comet's coma. Long, narrow plumes radiating from specific points on the surface, curving as if guided by magnetic fields. In natural comets, outgassing jets scatter chaotically. In 3I Atlas, they seemed aligned, almost geometrically. Computer enhancement of Hubble imagery revealed repeating angular patterns, though image noise prevented definitive conclusions. Nevertheless, the symmetry was striking enough for some analysts to describe it as engineered. This word, engineered, entered the discourse quietly, at first whispered in private correspondence, then debated openly in closed symposia. No one wished to jump to conclusions, yet the data resisted every conventional explanation. Could an ancient artifact, perhaps dormant for millennia, have reawakened under solar radiation? Could what we call a comet be something more complex? A vessel, a probe, or an automated sentinel left adrift in interstellar space? Astrobiologist Dr. Sanjay Patel of the Indian Institute of Space Science cautioned against such leaps, but admitted the parallels were haunting. If an autonomous system were designed to remain inert until triggered by specific environmental conditions, its activation could look exactly like this, he said. A rapid surge in energy output, emission of unusual spectra, reconfiguration of rotation, and signals indicative of internal power redistribution. We cannot rule it out entirely. The artificial hypothesis gained traction not because it was desired, but because natural alternatives grew increasingly convoluted. The need for multiple, simultaneous coincidences strained credibility. To explain all observations through natural processes required invoking delayed thermal conduction, impact by an unseen body, exotic chemical reactions, and synchronized outgassing, all occurring within hours of each other. The artificial model, by contrast, offered a single mechanism, the activation of technology. Still, scientists held to the principle of extraordinary evidence. Until material analysis confirmed artificial composition, alloys, manufactured geometries, or patterned emission in radio frequencies, the hypothesis remained speculative. Yet the weight of circumstantial evidence continued to rise. Across observatories, tension built. Observers stayed awake through consecutive nights, staring at live feeds, waiting for another shift, a flicker, a pulse, anything. In late-night telemetry rooms, conversations oscillated between wonder and anxiety. The sense that something intelligent might be unfolding beyond human control filled even seasoned researchers with quiet awe. Meanwhile, data analysts working on orbital simulations noticed a subtle change in trajectory. 3I Atlas appeared to have altered its orbit by a fraction of a degree. Negligible for routine dynamics, but measurable. The change could be explained by asymmetric outgassing, yet it occurred precisely as the thermal hotspots reached maximum intensity. The timing again was suspiciously coordinated. If this were propulsion, it was minimal but deliberate. A nudge rather than a blast. Public interest surged. For the first time in years, astronomy dominated headlines. Yet the official narrative remained cautious. Agencies around the world convened to pool data under the International Astronomical Union's emergency protocol. Specialists in plasma physics, spectroscopy, orbital dynamics, and artificial intelligence modeling collaborated in unprecedented unity. The central question guiding their inquiry was simple yet profound. What mechanism could produce correlated alterations in brightness, rotation, spectra, heat, and debris motion, all within hours? Each day brought more data, and with it, deeper uncertainty. If the event were natural, it revealed new categories of cometary behavior never before documented. If artificial, it represented contact not through communication, but through observation. The realization that something else had acted first. The distinction between discovery and encounter began to blur. Even the skeptics grew unsettled. A well-known critic of extraterrestrial hypotheses, Dr. Lewis Warren of Harvard, admitted during a press briefing, "We are forced to confront a reality that doesn't fit into our models." Whether it's geology, chemistry, or something beyond, 3I Atlas is teaching us humility. The ongoing observation campaigns now employ every major telescope capable of tracking the comet. Optical, infrared, radio, and X-ray. Deep space probes have been instructed to reorient sensors. The next weeks will determine whether the anomaly stabilizes or evolves. Scientists wait for patterns, repetition, modulation, or signals. The implications of either outcome are immense. If the transformation ceases, perhaps it was a one-time physical event, a natural yet extreme episode in cometary evolution. If changes continue, escalating in predictable ways, the argument for intentional activity strengthens. Already, algorithms analyzing the emission light curves have detected quasi-periodic oscillations suggestive of modulation, a pattern that, if confirmed, could indicate controlled processes. As the investigation deepens, one sentiment echoes through every lab, every observatory, every restless conversation beneath the glow of monitors. We may be standing at the threshold of a discovery that will redefine our understanding of nature, technology, and the boundaries between them. For now, 3I Atlas continues to shine, turning slowly in the cold dark, its newfound brilliance a message whose meaning remains hidden, perhaps a signal perhaps a mystery of physics, but undeniably something that demands the full measure of human curiosity and courage to unravel. The story of Three Eye Atlas does not begin with the recent transformation. Its origins reach back decades to the earliest photographic plates that recorded a faint, indistinct blur moving slowly through the star fields. At the time, it was catalogued without fanfare, one of thousands of icy wanderers populating the archives of the minor planet center. Its orbit was peculiar, inclined sharply relative to the ecliptic plane, suggesting that it came from far beyond the solar system's traditional boundaries. But even then, no one suspected it might one day become a focal point for one of the most profound scientific debates in modern history. Three Eye Atlas, formerly designated C2019Y4, was first seriously studied during its approach to the inner solar system several years ago. It appeared to be a typical long-period comet, its nucleus a frozen relic composed primarily of water ice, carbon dioxide, and silicate dust. Yet early spectrographic analysis already showed small peculiarities. The ratio of carbon monoxide to water vapor was unusually low, and the thermal inertia implied denser, more metallic inclusions than common cometary material. Even then, subtle clues hinted at difference, but the data were insufficient to spark serious reconsideration. The scientific community is cautious by nature. Anomalies are catalogued, not romanticized. After its first close passage, the comet fragmented. Small pieces broke away, producing a diffuse cloud that trailed behind. Observers assumed it was dying, fading into obscurity like so many before it. But fragments of Atlas continued to exhibit steady luminosity long after sublimation should have ceased. Some researchers noted this persistence but could not explain it. Others, like Dr. Emil Kaas at the Nordic Optical Observatory, kept the object under quiet observation. His logs show meticulous records of its faint photometric fluctuations, measurements that, in retrospect, seem almost prophetic. Something, he wrote, is maintaining structure within the debris field that should have dissipated months ago. When the recent transformation occurred, Dr. Kaas was among the first to recognize the magnitude of what he was witnessing. His voice, usually calm during transmissions, trembled as he confirmed the readings. He is emblematic of a generation of scientists raised on precision and skepticism, yet driven by awe. For researchers like him, this event has not merely altered data tables, it has shaken something foundational. The trust that the cosmos, vast though it is, remains predictable. The human stories behind these observations mirror the grandeur of the discovery itself. Across continents, astronomers have spent sleepless nights under flickering monitors, recalibrating instruments, questioning their assumptions, and rechecking their math. Every image, every spectral line becomes a potential clue in a puzzle that might redefine what it means to be alone in the universe. Within laboratories in Pasadena, Madrid, Tokyo, and Cape Town, young graduate students and veteran scientists alike have watched the same data curves rise and fall, united by a single sensation: wonder tinged with unease. The telescopes that now gaze at Three Eye Atlas are technological marvels in their own right. The Hubble Space Telescope, still operational after more than 3 decades in orbit, continues to provide high-resolution imagery from above the distortions of the Earth's atmosphere. The James Webb Space Telescope, with its gold-coated mirrors and cryogenic instruments, captures infrared signatures invisible to older observatories. Ground-based arrays such as ALMA and the Very Large Telescope fill in the gaps, offering radio and submillimeter insights into the material composition of the comet's emissions. Together, they form a global network of eyes, watching an object millions of kilometers away with a precision unimaginable a century ago. And yet, for all their power, these instruments reveal not certainty, but mystery. The more clearly we see, the more questions arise. The intricate thermal patterns mapped across the comet's surface now suggest internal architecture. The emission lines appear spatially confined, forming narrow bands rather than diffuse clouds. Computer models of the observed geometry yield structures that bear faint resemblance to hexagonal lattices, patterns not typically produced by random mineral crystallization. Some researchers quietly compare them to engineered radiative panels or heat dissipation grids. They do so carefully, aware of how easily imagination can outrun evidence, but unable to ignore the resemblance. If the artificial hypothesis were true, what could it mean? One possibility is that 3I Atlas represents a derelict probe, launched long before humanity's first steps into space, perhaps even before our species existed. Its materials, aged and scarred by countless eons, could mimic the disordered appearance of a natural body. Solar radiation might have powered dormant systems designed to awaken under specific conditions, a form of long-term autonomous operation beyond our current engineering capability. The recent activation could signify nothing more than a program executing an ancient directive. Observe, transmit, adjust trajectory. Others offer a gentler interpretation. Perhaps it is not a machine at all, but a natural entity performing acts that only appear intelligent because we do not yet comprehend their physics. In the same way that lightning once seemed divine before electricity was understood, this event might reveal processes that will one day appear ordinary. Our ignorance does not imply external agency, it simply marks the frontier of knowledge. Regardless of the explanation, the implications are profound. If natural, the discovery of new energy mechanisms or unknown states of matter within a comet's core would expand our understanding of planetary science, offering insights into how complex chemistry evolves in deep space. If artificial, then we stand on the threshold of contact, not through messages or symbols, but through the recognition of another intelligence's handiwork scattered among the stars. Either outcome elevates the human story. NASA's teams continue to operate with disciplined caution. Data are collected, cross-verified, and archived for open analysis. Independent observatories are invited to replicate findings. International collaboration, once slowed by competition, now accelerates under shared curiosity. The event has become a global experiment in collective discovery. For the first time in history, humankind is united not by crisis, but by the quiet pull of cosmic mystery. In the background of this global effort, whispers of philosophical reflection are growing louder. The notion that we might be witnessing either new physics